everyone. So today we're going to be going over some practice problems with acids and bases in water. So here's our first problem. Calculate the pH of a 1 molar H2SO4 solution, and it's given that the Ka2 is equal to 1.2 times 10 to the power of negative 2. So H2SO4 sulfuric acid is a strong acid, right? In its first dissociation step. So H2SO4 will dissociate into H plus and HSO4 minus completely. This reaction will go to completion. So in terms of finding the H plus concentration for the pH, this first step is going to be like the major producer of H plus. But there is a second step because it's a diprotic acid, so it can dissociate one more time. So HSO4 minus, and now we're going to use the equilibrium arrows, and then we have H plus and then SO4 2 minus. This step is the one which has this Ka2 of 1.2 times 10 to the power of negative 2. So the K of this reaction is equal to that. But like I said, this first reaction is going to be the primary producer of H plus. This one may add some H plus to it, but it shouldn't make a reasonable difference, like a significant difference. And I'm going to illustrate that with illustrating both of these reactions. One just with the first one, and with the first and second reaction. So first, we can just use this first reaction to find the concentration of H plus, right? Because since it goes to completion, we don't need an ice table, and we can just do dimensional analysis to find the concentration of H plus in the water. So if you have 1 molar H2SO4 for 1 liter, and then each H2SO4 molecule will donate 1 H plus in its first step. We're only considering the first step right now. And that gives you an H plus concentration of 1 molar. So if you were to go forward from here and calculate the pH, right, which is the negative log of the H plus concentration, you would get the pH to be 0. So that's only considering this first reaction, right? This one gives you a pH of 0. So now if you add the second reaction to it, right, it's not going to produce a significant amount, and I'll show you why. So we have this H plus concentration that we know is going to be there, like at least, right? Because this will go to completion. We know we have at least 1 molar H plus within the solution. So if you were to write out the ice table for the second reaction, right? We know the initial H plus concentration has to be 1 molar because we know that's what we have before this equilibrium reaction. The concentration of HSO4 minus is going to be also 1 molar, because if you do similar to this calculation over here, if we just substituted the H plus with HSO4 minus, we'd get 1 molar HSO4 minus. So we're producing both 1 molar H plus and 1 molar HSO4 minus. And then concentration of SO4 2 minus is 0. So this is going to be our initial and then the change. So because we have 0 SO4 2 minus here, the reaction is going to proceed towards the products. So we're going to produce SO4 2 minus and H plus, and then we're going to lose HSO4 minus. And then so for the equilibrium, it's going to be 1 molar minus X and 1 molar plus X. And then we have X here. So now we can use our Ka2 that they gave in the question, which is 1.2 times 10 to the power of negative 2, to find the concentration, find the X value of X. So Ka is going to be equal to 1.2 times 10 to the power of negative 2. And then you guys should also get into the habit of writing the expression as well in terms of the actual concentration. So you have H plus times SO4 2 minus over the concentration of HSO4 minus. And now we can substitute in the equilibrium concentrations. So we have 1.0 plus x times x over 1.0 minus x. And you also don't need to write the molar in the ICE table. We don't need to do that. Okay, so now we have to use our approximation technique. So first we're starting out with 1 molar, right? So if we were to add in 1 molar here, the small value of x isn't going to impact the 1 molar as much. So, and that's like basically why we only stick to the first dissociation step for the sulfuric acid. So we can approximate both of these to be 1 molar because the small x value isn't going to change it much. So this essentially is just equal to x because you have 1 molar times x over 1 molar, right? So all this just cancels out and you have x here. So 1.2 times 10 to the power negative 2 is equal to x. And we can also validate that with the 5% rule. So we have this over the initial concentration, so that's 1. And then times 100. And then this is equal to 1.2%, which is less than 5%, so we can approximate this to be approximately x. So now if we were to find our total H plus concentration, right? If this is x, our total H plus concentration is going to be 1 molar plus the value of x, right? Because of this here. So that would be 1 molar plus 0.012 molar. So notice how here, when we're keeping track of sig figs, right? We only have the tenths places here, but we have tenths, hundreds, and thousands here. This really small number isn't going to make a difference in the H plus if we're keeping track of sig figs. So this is just going to be 1 molar. And then this is basically what we had before over here when we only considered the first step, which is the pH of 0. So what we can take away from this is that whenever we have a sulfuric acid problem for like calculating the pH of a sulfuric acid solution, most of the time it's the first dissociation step that goes to completion is going to be the primary producer. So this is going to be the one that you should consider first. And most of the time, this is the only one that you're going to consider. The rule is that, however, if you have for concentrations, for sulfuric acid concentrations that are greater than, or that are 1 molar and greater, you only use the first step. And the second step isn't going to impact it as much. But if the concentration is less than 1 molar, then the second step does have a slight change that may impact the pH of it. And this makes sense because the less H plus you have produced from this first step, the more that this second step is going to sort of add to that. If you have a lot of H plus, then the small amount that's going to be added won't change it. And think of it in terms of equilibrium, right? In the second reaction, if we have a large initial concentration, right, that's going to push the equilibrium this way. But if you have a smaller one, then it's going to proceed more towards the products. Yeah. So the answer for the first one is going to be a pH of 0. Okay, so for our second problem, you have to calculate the pH of a 0.5 molar NaF solution, and we're given that the Ka of HF is equal to 7.2 times 10 to the power of negative 4. So first we can write out the reaction. NaF will dissolve in water completely, so we're going to produce F minus ions. And then this is going to react as a base with water. This is to produce HF and OH minus. So we can use a ICE table here to find the amount of OH minus produced, which we can use to also find the H plus and then the pH. So for the initial concentration, F minus is going to be 0.5 molar because it's in a 1-to-1 ratio and we have a 0.5 molar NaF solution. HF is going to be 0 and OH minus is going to be 0, and we're going to ignore the water because it's a liquid. For the change, we're definitely going to proceed towards the products. So this is going to be minus x, and this is going to be plus x and plus x. And equilibrium is going to be 0.5 minus x and x and x. So the KB expression, right? Because we're dealing with the base here. This is a base because it's accepting a H plus from water. So the KB expression is going to be HF times OH minus over F minus. Notice how in the question we're given the Ka of HF. So because HF and F minus are a conjugate acid-base pair, we can use Kw to find the Kb of F minus. So Kw over Ka is going to equal the Kb value. So if we substitute these values in, we have 1.0 times 10 to the power negative 14, which is the Kw, and then the Ka for HF is 7.2 times 10 to the power negative 4. And once we compute this, the Kb is going to equal 1.39. I'm going to keep an extra decimal place so that we remember to keep a few more sig figs and not like round in our calculator. So the check marks signify that only our final answer should only have 2 sig figs. I just kept the 9 after it so that we remember that we need to, when we plug into our calculator, that we need to take the entire decimal place and not round in between. 1.39 times 10 to the power negative 11. And this is going to equal this expression up here because that's a Kb value. So, and then now we can plug in our actual equilibrium concentration. So we have on the top we have x squared over 0.5 minus x. And then now we can use the 5% rule again. So this is approximately equal to x squared over 0.5. And we can solve for x, and we get that x is equal to 2.64 times 10 to the power of negative 6. So now we have to check to see if our approximation is valid. So we have 2.64 over times 10 to the power negative 6 over the initial concentration, which was 0.5, and times 100. And if you compute this in your calculator, you're going to get that it's less than 5%. So we can approximate this. So now this x value is equal to the concentration of OH minus, right? Because we had a Kb expression, so OH minus is equal to x. So now we have 2 different ways of finding the pH from here. We can use Kw again to find the H plus, or we can find the POH and then subtract it from 14 to find the pH. I personally like finding POH and then subtracting it better, so we'll just do that. But both ways work. So the POH is going to equal the negative log of the OH minus concentration, which is this value. And this is going to equal 5.579. And then we're going to keep track of this. So when we're using the logs, the sig fig rules only apply to the decimal places. So if we have this number technically has two sig figs, right? Our decimal place also has to have, well, we have to have two decimal places basically. We ignore this um, uh, one digit here. So if you have two sig figs, our decimal has two decimal places. We have two decimal places. If you have three, then we have up to the thousands place. So this is going to be our POH, and then we subtract that from 14 to find the pH. So pH is equal to 14 minus 5.579, and this is going to equal 8.42. And notice that at the end I'm finally rounding because this is my final answer to two decimal places. Okay, so for the next problem, it says calculate the pH of a 2.5 times 10 to the power of negative 8 molar NaOH solution. So typically when you have a strong base or strong acid, the first instinct is to convert this using dimensional analysis to find the OH minus concentration, and then based off of that you find the POH and then the pH. So at first I'm just going to try that and show you what it looks like, because like if we typically that's what we do, right? If we have a NaOH or other strong base, we're gonna find the OH minus concentration with dimensional analysis. So if I do that, I'm going to get that the OH minus concentration is equal to 2.5 times 10 to the power of negative 8, right? And then I get that the POH is equal to 7.60. And if I subtract this from 14 to find the pH, I get the pH as 6.40, and yeah, 6.40. So now you might be thinking, we added a base, a small amount of base into a solution, right? But when we do this, we're getting a pH that's greater than 7, like meaning it's an acidic solution, which doesn't make sense. So this is when we have to realize that NaOH isn't going to be like the primary contributor of OH minus or H plus ions in this case. Remember, we have to remember that the auto ionization of water also plays a role. In these previous examples, and most likely what you're going to counter, you're going to have a question where the acid or base is going to be the primary source of the OH minus or H plus. But in this case, because the OH minus concentration is so small, right, 10 to the power of negative 8, this is not going to be the major source of OH minus ions in the solution. So we have to use this along with the autoionization of water to determine the pH and POH. So water is going to dissociate into, so liquid is going to dissociate into H3O plus or H plus, either one works. And OH minus. So we have to label this. So our initial concentration of H3O plus is 0. Initial concentration of OH minus, we definitely have an initial concentration because we put this base into solution, right? Although it's not much, this could also play a role. Both of these could be acting together to contribute to the pH of the solution. So our initial concentration of OH minus is going to be 2.5 times 10 to the power of negative 8. And then we ignore this. So it's going to be plus x and plus x. So we get x and then 2.5 times 10 to the power of negative 8 plus x. So now the Kw is going to equal 1.0 times 10 to the power of negative 14, which is equal to the concentration of H3O plus times OH minus. And this is going to equal x times 2.5 times 10 to the power of negative 8 plus x. So now, typically what we've done before is we cancel this x out, right? Because it doesn't play a role, too much of a role on the initial concentration that we have. But in this case, we have such a small concentration of NaOH, right? We even determined here that it was such a small concentration because we got an acidic pH. So whatever is being produced with water will have an effect on the pH. So we have to include this. We can't ignore this and cancel this out. Because if we do this, then we're gonna get x equals we're gonna get that the OH minus concentration is gonna be this again, and we're gonna end up with 6.4 as a pH. So we can't cancel the x out here, and we just have to calculate it using quadratic formula. So 0 is going to equal x squared plus 2.5 times 10 to the power of negative 8 times x minus 1.0 times 10 to the power of negative 14. So I just moved this term to this side, subtracted it, so I got it in the correct form that we need to do the quadratic formula. So minus b is going to be minus 2.5, this is x equals 2.5 times 10 to the power of negative 8 plus or minus the square root of b squared minus 4a, which is this 1, c all over 2a. So a is just 1, so 2. And once you compute this, you would get that x equals to 8.83 times 10 to the power negative 8. And the x in this case is going to be the H3O plus concentration, because that's equal to x. times 10 to the power negative 8. And now we can use this value to calculate the pH. Which is a negative log of this value. And once we do this, and we use our proper sig fix, we get that the pH of the solution is 7.05. So this makes sense because it's super close to 7 because we had such a small concentration of NaOH added to the solution, right? So that makes sense. And also it's super slightly basic because we did add NaOH after all. We didn't get an acidic pH like we did before because we considered the autoionization of water. So yeah, that was a little bit of a tricky problem because typically for strong acid and strong base problems, we skip straight to calculating the H plus or OH minus concentration with dimensional analysis, but we have to take a step and understand like which species is producing is going to be the major source of the H plus or OH minus in the solution. In this case, water, along with the NaOH, played a significant role. So yeah, I hope that video was helpful, and thank you for watching.